Hello everyone. In this video, we are going to solve worksheet number 13, which is mostly about L'Hopital's. As the first example, we're going to find the limit of x squared minus x over x squared minus 1. You may think of L'Hopital at the first time, but usually you don't know or you're not sure about that. So we would do it, or we can do it without L'Hopital also. So one of the basic ways that we usually find the answer for limits is factoring or using algebraic methods. For this one, for the top, we can factor out x, and then we're left with x minus 1 over the denominator can be factored as x minus 1 times x plus 1 when x is approaching to 1. So you would see that we can cancel these two, and then after plugging in 1 for x, we would have uh, x over x plus 1 before plugging in. And here we are allowed to do direct substitution. So we would have 1 over 1 plus 1, which is 1 over 2. And we could find this limit without L'Hopital, but you can do the L'Hopital also. Okay, for the second one, it is when you plug in infinity, you would have infinity that e to the x is a function that grows faster than power function, as we had in the lecture. So basically, when it is infinity minus infinity, we are going to use some methods in order to use those methods and find the answer as an amount which is defined, not undefined. In here, the trick is, since we know e to the x grows faster than power function, in here we know that the power is just 1, so we can say that the answer is infinity. Next one, if we think of plugging in infinity, it will be ln of infinity, which is infinity over infinity. So one of the ways that we can find the limit is using L'Hopital, finding the derivative of the top, which is using chain rule. We would think of this as if it was x squared, I would write it as 2x, but in here I have ln of x squared. So I would write it as 2 ln of x times derivative of the inside, derivative of ln of x, which is 1 over x. And derivative of the denominator is just 1. So we would check if this is defined or not. Whenever you use L'Hopital, please write that here. This one, when you plug in infinity, you would again have infinity as the answer. So if you simplify, you would get 2 times limit of ln of x over x, because we have to write it in a way that we can use limits, L'Hopital. In here again, we have infinity over infinity, so we can use L'Hopital's. 2 is just here as the coefficient limit of the amounts that are going infinity. So the derivative of ln of x is 1 over x. Derivative of x is 1. We would have 2 limit of 1 over x when x is approaching infinity. And we know that this one is 2 times 0 equals 0. Next one, number 4, when you plug in 0, you would get e to 0 minus 1 over 0. We know that any number, including e, which is 2 point something, would be, to the power 0 would be 1 minus 1 over 0. So we have 0 over 0. And we're allowed to use L'Hopital's here. We would take derivative of numerator, which is again using chain rule. So we would have 3e to 3x over derivative of t, which is 1 when t is approaching to 0. Now we are going to have 3e to 0, which is 1, and altogether we would have 3 as the answer here. Number 5 is finding the limit of this fraction here. Again, we would check it out if it is defined when you plug in 0 or not. We would get e to 0, which is 1, minus e to negative 0, which is the same as e to 0, minus 2x, which is 0, over x, which is 0, minus sine of x, which is 0. So 0 minus 0. We would have 0 over 0, and now we think of using L'Hopital. We would have limit derivative of the numerator. We know that derivative of e to x is e to x minus derivative of e to negative x is a copy of itself times derivative of the power, which is negative 1. So I would write positive because negative times negative would be positive. Derivative of negative 2x is negative 2 over derivative of numerator. We know that derivative of x is 1 minus derivative of sine is cosine of x. Now, we would check if it is defined or not. When you plug in 0, you would have e to 0, which is 1, plus e to negative 0, which is 1, minus 2. So it will be 1 plus 1 minus 2 over 1 minus cosine of 0 is 1. So we again would have 0 over 0. So we would use L'Hopital again, limit of derivative of e to x is itself, derivative of e to negative x is negative e to negative x, as we described before. The derivative of 2 as a constant is 0, and numerator derivative of 1 is 0, minus derivative of cosine, which is negative sine of x, when x is approaching to 0. Again, when we plug in 0, we would have e to 0, which is 1, minus e to negative 0, which is 1, over sine of 0, which is 0. So again, we would have 0 over 0, and it is time to use L'Hopital again. Taking derivative of the top gives us e to 0 plus e to negative x, because it would be e to x minus negative e to negative x, which is positive, over this one is sine of x, and the derivative is cosine of x when x is approaching 0. So this time e to x, which is 0, is 1, plus e to negative 0 is 1, over cosine of 0 is 1, and it is defined. So the answer is 2. Number 6, when you plug in negative infinity, you would have infinity times e to infinity, which is 0. So one of the ways that we can find the limit when we have 0 times infinity or infinity times 0 is using L'Hopital. But in order to have L'Hopital, or in order to be allowed to use L'Hopital, we would have a fraction like 0 over 0 or infinity over infinity. We would use one of the ways that we can do. Sometimes one of them works, sometimes both works. It depends. In here, if we write x squared over e to negative x, when x is approaching negative infinity, we would see that it would be 0 it would be infinity over infinity. Now we can use L'Hopital. So limit derivative of x squared is 2x, derivative of e to negative x is negative e to negative x when x is approaching to negative infinity. Again, it will be infinity over infinity. So we would use L'Hopital, which will be limit derivative of 2x is 2, derivative of negative e to negative x is positive e to negative x when x is approaching negative infinity. So we would end up 2 over infinity, which will be 0. Number 7 is sine of x times ln of x. We know that sine of 0 is 0. We know that ln of 0 approaching to right side of 0 because left side of 0 and 0 is not defined in the function ln. So when x is approaching 0 to the right side, if you don't remember, this is the graph for ln of x, and this is the asymptote. So right after 0 would be 0 plus, and this one is going to negative infinity. So we would have 0 times infinity, and we are going to use L'Hopital, but before that we would have a fraction as infinity over infinity or 0 over 0 to be allowed to use L'Hopital. Okay, I will write limit of ln of x over 1 over sine of x. Because if I write it this way, when x is approaching to 0, but right side of 0, it will be limit of ln of x over cosecant of x because of the definition of 1 over sine x approaching 0 plus. We know that the definition says whenever you have 1 over sine of x, it is cosecant of x. Now we are allowed to use L'Hopital because it will be infinity over infinity. So limit of derivative of ln of x is 1 over x. Derivative of cosecant of x is negative cosecant of x cotan x when x is approaching 0 plus. We try to simplify here. In order to simplify, I can rewrite it as negative limit of 1 over x, 1 over sine, because of the definition of cosecant, times 1 over cotan. You may think of not writing cosecant at all. It's your choice. You may find finding derivative of 1 over sine hard to do, so you would like to see it as cosecant and then take derivative in the previous step. But maybe you would like to keep it as 1 over sine of x and then use the quotient rule in order to find the derivative. It's your choice when x is approaching 0 plus. So after simplifying, I would have negative of limit of sine of x over x times, we know that 1 over cotan is tan x when x is approaching 0 plus. And based on the limit laws, we can separate these two to write it negative sine of x over x times limit of tan x. And we know that limit of sine of x over x when x is approaching to 0 is 1, and limit of tan when x is approaching to 0 is 0. So altogether, the answer is 0. Number 8 and 9. Number 8 is about finding the limit of sine of 4x over tan 5x. We know that if we find the limit, it would be 0 over 0. So we try to use L'Hopital. Limit of the derivative of sine of 4x is 4 sine of x using the chain rule. And derivative of tan 5x is 5 secant squared of 5x using the chain rule when x is approaching to 0. And we know that sine of 4, I'm sorry, this one is cosine. Derivative of sine is cosine. We know that cosine of 0 is 1, and we know that cosecant of 0 is 1 because secant, because secant of x by definition is 1 over cosine of x. When x is 0, it will be 1 over cosine of 0, which is 1. When x is approaching to 0, so we don't need other stuff, but we need the coefficient because we have 4 here, we have 5 here. 4 over 5 is the answer, and also you don't need to write limit as well. Number 9, when you plug in pi over 2, you would get 1 minus sine of pi over 2, which is 1, over cosecant. Cosecant by definition is 1 over sine. And sine of pi over 2 is 1. So 1 over 1 is again 1. We would have 0 over 1, which is defined. So there is no need to use L'Hopital here. Next one, number 10. Rank the functions in order of how quickly they grow as x approaches infinity. There are many, not many, there are a couple of ways that you can approach this, but sometimes it is easier if we write the functions in a form that we can decide between them. So the first one is 2 to the x, the second one is 3 to the x, which are both exponentials. And the third one here is e to x over 2. We know that we can rewrite it as e to 1 over 2 and to the power x. We know e is a number, and using calculator, we can rewrite it as 1.65 to the power x. So keep it this one. The first one was 2 to x, the second one was 3 to x, and the last one is also y equals e to 1/3 to the power x, which can be approximately 1.40 to the x. Now, that all are in terms of exponential, we can say that exponential functions grow faster as the base increases. So you can try drawing the graphs for, this is a typical way that we write exponential functions when a is more than 1. And this is the tip, and something like this is a typical, not like this, because they should cross each other at 1. This is when a is between 0 and 1, but we don't have that here. So when you try different numbers as the power, as the base, you would see that exponential functions grow faster as the base increases. So if this one is 2 to the x, the other one is 3 to the x, and 1.65 is less than 2, 1.40 between all these, and you would end up with this order. 3 to the x grows faster than 2 to the x, grows faster than e to x over 2, grows faster as e to x over 3. We could do this because all of them was All of them were in form of exponential. But if we have different kinds of functions, we cannot do it in this way. Number 11 is a word problem. Please pause the video, read the problem, and then listen to the solution. Okay, based on the information that we have here, when k is approaching to 0, 1 minus e to negative k is also approaching to 0. We know that any number to the power 0 is just 1, so 1 minus 1 is approaching to 0. And then we can apply L'Hopital's rule. Limit of c, which is limit of r over k, times, let me correct this one. Limit of c when k is approaching 0 is limit of r over k times 1 minus e to negative k when k is approaching to 0. So if we want to use L'Hopital, we need 0 over 0 or infinity over infinity. So it would be a good idea if I rewrite it as r times 1 minus e to negative k over k to have 0 over 0. So using L'Hopital's rule, we would take derivative of the numerator and denominator. So we can write r here as the coefficient, which is not depending on k. So limit of, if we take derivative of the numerator, it will be 0 minus negative e to k. So we would have e to negative k over derivative of k with respect to k is 1 when k is approaching to 0. So we have r, and we know that e to k is 1 because k is 0, e to 0 would be 1, and then r is the answer. And what is the interpretation? The interpretation based on the information that we have is the upper bound for the concentration is R, the same as the injection rate. Okay, we will move to the next one, number 12. Again, since it is a word problem, please pause the video and then after reading the question, listen to the solution. So when t is approaching to infinity, we would see that e to negative 0.0467 t is also approaching to 0 because e to negative infinity is 0. So for c of t, if we take limit, we would have 0 times infinity. And this means that we can use L'Hopital, but we have to write it as a fraction as infinity over infinity or 0 over 0. So limit of c of t when t is approaching infinity will be limit of 0.0225 t e to negative 0.0467 t when t is approaching infinity. In order to write it as a quotient, we can move the power to the denominator. So we would rewrite it as 0.0225 t over e to positive 0.0467 t when t is approaching to infinity. Now we can take derivative and we would use L'Hopital rule here. We know that the derivative of the top is 0.0225 over, okay, this one here is correct. Will be the power as the coefficient, so 0.0467 times e to 0.0467t when t is approaching to infinity. So it will be a number 0.0225 over infinity, which means that the answer is 0 here. Next one is not here. Okay, we will do the next one in another video.